Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Fatihah binti Abdul Hadi. In this video, I would like to present my final year project entitled Effect of Pva-Peg addition on Microstructure and Mechanical Properties of Zirconia Tapan Alumina infused with empty foot bunch derived solid carbon. But before that, I would like to thank Dr. Zahirani and Dr. Hanisa for letting me to conduct this project. In this video, I will explain on the introduction, problem statement, objective, literature review, methodology, as well as conclusion. As for introduction, aluminum-based ceramic has been widely used for the cutting tools because it owns some excellent properties such as high hardness, high melting point, high wear resistance, high compressive strength against high temperature, as well as low cost. However, aluminum-based cutting tool possesses one main drawback, which is brittleness due to its low fracture toughness, which in turn leading to the sudden damage of the cutting tools during the high-speed machining due to the crack propagation occur in the materials. So it is shortening the life of the cutting tools. Then, the emergence of ZTA has received significant attention as it possesses high hardness, high strength, high fracture toughness compared to the monolithic aluminum ceramics. ZTA is developed by reinforcing the aluminum matrix with stabilized zirconia particles in order to exhibit the toughening mechanism. And the previous study stated that in order to obtain the best wear resistance and improve the mechanical properties of ZTA, the best composition ratio between alumina to yttrium stabilized zirconia is 80 to 28%. It is shown that the fracture toughness is increased. However, the hardness of material is decreased. The fracture toughness of ZTA is further increased by reinforcing with the carbon nanotubes. This is because carbon nanotube own some excellent properties such as very high tensile strength, which is over 100 MPa, high elastic modulus, which is 1.28 TPa, as well as good electrical and thermal conductivity. Unfortunately, even though the fracture toughness of ZTA reinforcing by CNT is increases, the hardness is decreased. Hardness decreased because of the presence of SWCNT lead to the agglomeration in ZTA composites, which act as a weak spot that does not provide an improvement due to inability to carry the load. The problem statement of the study is that during the fabrication process of the ZTA reinforced with carbon nanotube, such as by using hot press sintering, most of the carbon nanotube will damage due to the high temperature processing. And the second one is CNT tends to agglomerate, which later produces a weak spot, thus reducing the hardness of the material. And the third one is some methods have been done to solve this problem, such as by using spark plasma sintering (SPS). However, this process requires very higher cost as high amount of energy must be used. So the objective of this study is to design the microstructure of ZTA through the addition of suitable amount of polyvinyl alcohol and polyethylene glycol in order to achieve optimum porosity. And the second one is to optimize the amount of solid carbon infusion into the sintered ZTA in order to obtain better mechanical properties in terms of fracture toughness and hardness. And the last one is to evaluate the microstructure and mechanical properties of ZTA with the addition of PVA and PG and infused with the solid carbon from EFB. Polyvinyl alcohol, PVA, and polyethylene glycol, PEG, are the most well-known binary used in ceramic systems. According to Carton and Norton 2007, PVA provides a high green strength while PEG provides a high green density to the ceramics. This figure shows the results on tensile strength versus sintering temperature for alumina samples prepared from 0 to 3% PVA. According to Takta et al. 2011, at any sintering temperature, samples prepared from 1% PVA owns larger mechanical strength compared to those prepared from 3% PVA. This is because a better densification is achieved by the samples containing less amount of PVA. For the samples containing 3% PVA, it has relatively high cohesion and become hard to be distorted. Thus, during the compaction, it cannot be deformed easily. So that's why in this graph it shows that the sintering temperature of the obtained compact is shifted at high temperature. In this table, it is clearly shown that the sample prepared from 1% PVA powder shows higher relative density than those prepared from 2% PVA powder. This is actually due to the better densification achieved by the sample containing less amount of PVA. According to Beclotti et al. 2001, the spray-dried alumina powder incorporated with PEG gave a higher degree of flexibility and results in the homogeneous microstructure of the sintered body. Therefore, once the binder burns out at elevated temperature, pores are uniformly distributed throughout the pellets and lower density pellets can be obtained. This results in the production of porous alumina ceramides containing well-formed and homogeneous pores. For this result, it is stated that the grain density of the sample with a content of 5% Pg is the lowest compared to the other sample with 0 to 4% Pg. This is because too high percent of Pg will cause the granules to move rapidly and results in re-enrichment when the alumina powder grains are pressurized. As a result, the densification is reduced. So the optimum content of PEG must be known in order to increase the grain density of the alumina pellet. This figure shows the evolution of the tensile strength versus internal temperature for alumina samples prepared from 0% PVA or PEG, 3% PVA and 3% PEG. And it is stated that the addition of 3% PEG to the alumina results in soft and more deformable granules compared to the alumina with 3% PVA. This is because PVA has higher glass transition temperature than the pressing temperature. Okay, pressing temperature is at room temperature and the glass transition temperature of the PVA is 79 degrees Celsius. So in this condition, granules become hard and difficult to distort, thus not sufficiently soft in compaction. This results the relative density of alumina compact with 3% PVA to be lower compared to the alumina with 3% PEG. Simultaneously, its tensile strength is lower too. According to Zara et al. 2019, once plasticizer molecule distribute between the binder's polymer chains, it will disrupt the alignments and decrease the van der Waals forces among the neighboring chains, so the polymer will be packed less tightly. Therefore, it does soften the binder and leads to enhancing of its flexibility. From these figures, it can be inferred that due to the plasticizing effect of PEG on PVA binder, the property of alumina is improved back compared to when using the PVA binder alone. What I mean is that 3% PVA and 3% PEG is the best binder composition as it gives the highest tensile strength of alumina, which is at 129 MPa. Active fruit bunch (EFB) is one of the biomasses produced by the oil palm industry, available in Malaysia. And this organizing of this waste, such as by biomass dumping, can cause change of the environment due to the natural methanation cycle. And according to Pva-Peg et al. 2018, EFB-derived biochar has been used in previous study in order to sinter the iron ore with regards to the porosity of iron sinter and its further application in ceramic composite. The first part of the methodology is to obtain porous sintered ZTA pellet by using 3% PVA and varying 0 to 5% PG, and then press using hydraulic hand press and sintered at 1600 degrees Celsius. The second part is to infiltrate the solid carbon into the pores of ZTA by using CVI process. But before that, EFB was dried at 109 degrees Celsius for 24 hours in order to eliminate its moisture content. During CVI, the tar vapor will be infiltrated into the pores of ZTA to form the solid carbon and also gaseous species. And then the solid carbon will deposit on the surface of the pores, while the gaseous species will leave the pores. Okay. The temperature is set to 500 degrees Celsius with the holding time of 1 hour. This is because to avoid to reduce the colliding molecules during the tar water vapor decomposition. So at the end, physical and mechanical characterization is done in order to evaluate the microstructure and also the mechanical properties of the sintered ZTA pellet infiltrated with the solid carbon from EFP. So in conclusion, to achieve high fracture toughness and high hardness of ZTA, the optimum porosity is required to allow the infiltration of the carbon into the ZTA. And it is expected to produce optimum porosity of ZTA by altering the plasticizer and binder composition to produce less dense and porous composite. SRD, scanning electron microscopy, beds and Raman could be used to further characterize the sintered samples, microstructure, and fracture toughness and Vickers hardness tests can be used to evaluate the mechanical properties of ZTA samples before and after the carbon infiltration process. And lastly, this is my Gantt chart. I think that's all from me. Thank you.